Welcome back, everyone, into lecture 7 of our fundamentals of tailings engineering short course put on by Taileng. We'll wait just a minute here for all the attendees to populate, and then we'll get started. All right, I see us approaching the 50 mark, which has been our benchmark for starting for the last number of talks. So we'll keep it on there. So welcome back, everyone. We are in lecture 7, in introduction to tailings geotechnics. I'm very happy to welcome in Professor Scott Olson, my colleague in Taileng, visiting us online here from University of Illinois Urbana-Champaign. So Scott, thanks so much, and I'll hand it over to you.
Sounds good, Chris, and thank you. And welcome back, everyone. Let's see, what are we going to talk about today? It looks like we have had a fantastic course that Chris has put together for us so far. We are now down here to the Intro to Tailings Geotechnics, a topic that is very close and near and dear to my heart. So I won't spend much more time on this slide. What I do want to highlight here is that each of these lectures, hopefully, we have been addressing some key questions. Now, I know this is very small, so I blew up the questions there related to topic 7. And that is what I want to kind of cover here and address is, when does tailings geotechnics become important? And what are the similarities and differences between soil and tailings engineering? As you'll see, there are an awful lot of similarities, and we'll use a lot of the same terminology when it comes to geotechnical engineering of tailings, and there will be a lot of overlap with other geotechnical courses, other geotechnical knowledge that you might have. And then lastly, what tailings geotechnical behavior is important for the evaluation and physical stability of a tailings facility. So there are a lot of topics that we could cover in an intro to tailings geotechnics. I'm going to focus on just a few items that I consider are key importance for evaluating tailings facilities. So what do I hope that you get out of this course? Firstly, understanding the development of stresses in tailings impoundment. Next, one of the key behaviors that I want to cover is consolidation behavior, because I think it's very important to be able to understand and, more importantly, predict consolidation behavior of tailings in order to differentiate it from the volumetric response of tailings during shear. Next, I want to talk about strength and deformation characteristics, that is volumetric deformation characteristics during shear under both drained and undrained conditions. And then I'll very briefly, as an introduction to our next lecture on critical state soil mechanics, very briefly describe that framework that connects stress, density, and shear behavior, and identify some of the common loading conditions that you might encounter in tailings facilities. So as you've probably seen similar slides already during this short course, tailings can vary across a continuum in terms of solid content or water content, if you prefer, from slurried tailings over here where the solid contents are relatively low, water contents are going to be very high. And you can see these are flowing as a fluid that has some solids in them. As you start to dry out the material and increase the solids content down to, say, 15 or 20%, you get to the point of filtered tailings on the other end of our spectrum. I'm going to focus this talk starting from this end of the spectrum, that is slurried tailings. And I want to highlight something that's quite important here for geotechnical engineers. You should be familiar with these terms, others might not. But if we're discharging by pipeline, by slurry, mine tailings into an impoundment, and that solids content is right in the middle of that range that I just mentioned for slurry placement, about 35%, your water content is going to be on the order of 190%. So this is a very fluid material that's at first not going to behave much like soils. It's going to behave as a viscous fluid. And that's why we use viscosity rules, and we use different mechanics to understand flow of these tailings through pipelines. We're going to talk about how it then transitions from that slurry into more of a soil. If we start on the other end of that spectrum with filtered tailings, your water content might be on the order of only 20%, meaning that the soil is mostly solids, about 83% solid content at that point. And again, that is the point that we want to get the tailings to through consolidation processes. Now, what are the benefits or pros and cons of starting at different points along this spectrum of water contents or spectrum of solid contents of tailings? As we know, slurry tailings or placing tailings via pipeline is fairly inexpensive. It's much easier to transport, reduces processing. However, on the downside, of course, we start out with fluid tailings, very low strength. There's going to be a lot of consolidation. Because we're storing initially a lot of water, we need large space or large storage volumes. And we're going to need those structural perimeter structures in order to contain that fluid tailings. On the other end of the spectrum are filtered tailings. You're taking out most of the water at the processing plant. Therefore, as it is placed, it's going to have much higher strength and going to consolidate much less. It's going to be almost immediately trafficable, and behaviors might be a little bit more predictable. The downside is that there have been very few applications where this has been done at very large scales. It's also the most expensive and most energy intensive because you're using various methods to either squeeze or dry that water out from the material that's being processed. You also you can't transport this by pipeline anymore. You've got only a few options for transporting the material. Now, of course, from one end of that spectrum to the other, we're going to lower the risk because here we're starting with material that has higher strength in terms of the overall performance, particularly in terms of stability of the structure. So when we start from that slurry, we can use knowledge from our hydrotechnical friends, our hydrologists and hydraulics engineers to help us understand what is going on in that impoundment. And so if we think about this from a hydrotechnical point of view, we have our substrate here that is lower levels of tailings that have already been placed, and we have material that is going to move and be eroded as the pipeline is depositing material at a particular point. And then, of course, pipeline spigots may get moved around your facility. You're going to erode the upper layer. So you've got a layer of material that is going to move or be erodible during the next portion of the depositional process. The slurry that's being placed is going to contain a number of larger particles, at least initially, as well as smaller particles such as clays that will be suspended in the fluid, and potentially dissolved ions, flocculants, and other additives that come from the processing plant that are still in that flow. So our process really then is one of saltation along the bed here, where smaller particles, but large enough that they cannot be carried is suspended load, are going to bounce around on that bed of material here on the substrate and on this surface until they find a spot where they get locked in place. Our suspended load is going to continue to travel with this fluid until the fluid velocities reach near zero values. In other words, this fluid reaches the pond, and then the finer materials can finally settle out. So in terms of our definitions here, I mentioned substrate, I mentioned bed load or suspended load, and that dissolved load. All of these are characteristics of traditional hydro flows and also characteristic of flow into a tailings impoundment from slurry deposition. Now, in terms of the velocities, I mentioned velocities being an important aspect of how material is either eroded, transported, or deposited. And this Julstrom diagram has been around for quite some time. You see the original was developed by a Julstrom back in 1935. So about 90 years or so ago, this concept has been around to help us understand what is going to be deposited and so on. We're focused primarily down here in medium to fine sands and finer materials. So you get an idea here of our velocities of discharge from these spigots or from our pipelines into the impoundment, and what range of particle sizes are going to be deposited, what range of particle sizes are going to be transported, and here at high flow rates, right near the discharge points, what size particles are going to be eroded and transported further upstream. Because of this concept that we've got our highest velocities here, and immediately the velocities start to decrease and further decrease as you go further upstream, more and more of the fine particles are going to start being deposited as these velocities decrease. And that gives us this conceptual diagram for the stratigraphy of a typical tailings facility. So here you have your starter dikes and your raises at the deposition points, typically going from one of these exterior or perimeter dikes being deposited inward. The coarsest materials, so your medium to fine sands, are going to be deposited closest to the discharge points. We then go through a transitional zone where siltier material is being deposited, and then toward the inner portion of the facility in the ponded area, where the finest tailings and slimes, or ultrafine tailings, that is your clays and very fine silts, will be deposited. Now, of course, this is an ideal scenario of decreasing grain size toward the inner portion of the facility, increasing permeability toward the outside of the facility. But again, this is idealized, that when you have very heavy materials that are being deposited, iron ore as an example, the material may have a high enough specific gravity that those fines can be mixed in with the coarse material and deposited, such that we don't get these very nice zones, if you will, idealized zones. And in addition, as the spigots are moved around, your pipelines are moved around, you may have at one point water ponded near one side of the facility, and then at a later date, water ponded near the other side of the facility. So you often get much more layered stratigraphies than what is illustrated here in this idealized stratigraphy. In terms of how that material transitions from a slurry to a soil, it's going to, tailings again are going to behave an awful lot like natural soils that are transported via water, alluvial soils. That is, we're often going to see a stage of what we call flocculation. That is, those additives or flocculants that may have been added at the processing plant that are still in our slurry, they may be positively charged and attracted to negatively charged particles. A lot of silica-based particles have a net negative charge on their surface, and so they are attracted to, or I should say these flocculants are attracted to the surface of these particles, and that creates flocks of material that then become ultimately heavier as those flocks start to grow into larger flocks. And this is just an example of kaolinite minerals that have been flocculated. So you see here the individual, this is actually 2 layers of kaolinite particles here, but you can see how these have flocculated together due to the addition of positively charged ions in this pore fluid, creating these larger flocks of these minerals. And as a result, as a result of this flocculation process, these minerals or these particles now become larger and heavier and may again settle out before they reach those idealized zones from the coarsest to the transitional zone to the finest zone in the ponded area. Now, of course, as they become heavier, they start to settle out of suspension and form a settlement layer that is going to start to consolidate. And that's the process of this slurry now becoming a soil. And once again, the soil doesn't know that it is a mine tailings oftentimes versus a natural deposit. So many of these processes are quite similar. One of the key differences, though, is your geochemistry. The chemistry coming out from a processing plant commonly is quite different than what occurs naturally. So as geotechnical engineers, we also need to have that geochemistry toolkit in or that concepts in our toolkit to help us understand how this transition, how this flocculation, settling, and consolidation behavior are going to occur. These are all time-dependent processes and the duration of each of these processes, from flocculation occurring over a certain amount of time, the settling occurring over a certain amount of time. And so this is both plotted in terms of time and here as elevation, that as the material moves farther inboard or upstream, we're going to get a zone where settlement occurs, or we start seeing settling of those particles, and then a zone where we start to get consolidation under a certain amount of additional weight of those particles settling down. And as I mentioned here, the duration of each of those stages is going to largely be a function of the particle size as well as the chemistry of the pore fluid. So once again, geotechnical engineers, our mining engineers have to have a little bit of geochemistry, an understanding of that geochemistry to really understand this process well. Now, dispersed particles, ones that do not flocculate well, whether that is due to the particles themselves and their net charges or due to the types of geochemistry that is present, are typically not going to settle, even after long periods of time, simply because there's not enough quiescent time in ponds in most facilities. So these are those particles that may include our dissolved ions and other types of very fine particles that never do settle out. They exhibit more of a colloidal behavior and follow different physics. Now, we're going to focus the rest of our time here on talking about the key geotechnical properties of this material as it goes through that settling and into the consolidation stage. Now, I like to break up my key geotechnical properties into first index properties, things like I mentioned a moment ago, water content, which can be measured either volumetrically or gravimetrically, where the gravimetric water content is the weight of the water in a given volume of material versus the weight of solids in that same volume of material. We also use things like the Atterberg limits to help us describe different types of behaviors. You've probably heard the term plasticity before. That is related to the Atterberg limits. These are water contents at which behaviors start to change. Void ratio is another very important index property, both the minimum and maximum void ratios that relate to how loose or how dense that material can be given its gradation, its mineralogy, and its plasticity, as well as the actual void ratio in situ. We also often use relative density as a term to describe where that void ratio falls in between the maximum and minimum void ratios. But we know that relative density often is difficult to determine for finer soils or silts and slimes. So often we simply use void ratio, which is an indicator of how much void space we have in a given volume of material. And specifically, this is volume of the voids divided by volume of solids. What I want to focus on, though, is engineering properties. And engineering properties, I typically break up into three key properties. That is the permeability or hydraulic conductivity, and that's going to differ depending on the saturation conditions of the soil, whether that soil is fully saturated, partially saturated, or completely unsaturated. You will get very different values of permeability or hydraulic conductivity. The consolidation or compressibility characteristics. So you might also hear this term stiffness or modulus, which is simply the inverse of compressibility. We often use things like compression index or pre-consolidation pressure. We'll talk a little bit more about this one because this relates to that settlement behavior that we would expect to see during the consolidation phase as this soil or as this material transitions from a slurry to a solid and becomes more and more solid as we pile more material on top of it. And lastly, perhaps the most important one for tailings facilities is shear strength. And we'll talk a little bit about drain shear strength, undrained shear strength, and critical state shear strength. Now, I separate these, and what is unique about geotechnical engineering is these engineering properties all are a function of what we call effective stress. And I apologize for those geotechnical engineers in the audience who should have a very firm understanding of effective stress, but it never hurts, even for good geotechnical engineers, to review effective stress. So I'm going to just briefly review the concept of effective stress, because all of these engineering properties, including the two that I'm going to focus on, consolidation and shear strength, depend so heavily on that effective stress. So let's start with the simplest one, defining what we call total stress in a soil. So total stress, and here I'm using a subscript V to indicate this is total stress in the vertical direction, or simply total vertical stress, is the weight of some column of soil. And here I'm using a unit area of soil. So 1 unit length by 1 unit length down to a depth Z below the ground surface. This column is going to have a certain weight, and the stress, therefore, is going to be defined as that weight divided by this unit area. So again, we call that the total vertical stress. We can calculate the weight if we know the unit weight of this material. If we take that unit weight of soil, which is density times the acceleration of gravity, so this gamma term here is rho, density times g, the acceleration of gravity. If we take that unit weight, multiply it by our depth, multiply it by the unit area, we get our weight, divide by the unit area again, and we can then simplify this calculation for total vertical stress as our unit weight times depth. When we have layers with different unit weights, of course, this is just going to be additive, and so we sum up the unit weight times the thicknesses of different layers to get the total stress at any particular point. One thing I want to note is that we commonly in geotechnical engineering use a engineering area, not the particle to particle contact area. And why we do that will come clear here just in just a moment. The next stress that's important, particularly in tailings facilities, is the water pressure, which often is termed a neutral stress if there is no flow occurring. And that water pressure is simply defined as the unit weight of water times the pressure head in the water. So this goes back to your understanding of Bernoulli's equation and hydromechanics and hydrodynamics that I personally had some trouble with, had struggled with for a while as a student. It's now just finally starting to come clear in my mind many years later after teaching it for many years. But we can take the unit weight of water, multiply it by the pressure in the water as defined by some head, and get that water pressure. Now, I call it neutral stress, or many engineers call this a neutral stress, because water pressure increases linearly with depth if there is no flow, and it acts equally in all directions. In other words, it is a neutral stress. It's not higher in going this way or this way, going up or down when you are talking about pressure at a given point. It acts all the same, or the same in all directions if there is no flow. However, there may be flow occurring in many tailings facilities. There may be flow toward the perimeter dikes. If you've got a permeable foundation material, there may be flow vertically downward through the tailings. And so in those cases, we have to account not just for the static or hydrostatic conditions, but also for the effect of flow on the water pressures in the soil. Now, we can still use that same equation. The water pressure is still the unit weight of water times the pressure head, but that pressure head is going to change when we have flow going through or moving through the material. And I like to explain this in a very simple manner. That is, we know from hydrology and hydromechanics again, that as water flows through a pipe, for example, there are going to be shear stresses or drag stresses along that contact due to the fact that no interface between water and any engineered material is perfectly smooth. There's always going to be some roughness, and therefore there's always going to be some friction that occurs. That friction can be called a drag force. So you've got water flowing around these particles, and as it flows around these particles, there's shear stresses being developed at that interface, and that shear stress is acting to pull the particle, or push, if you will, the particle in the direction of flow. So it is changing the stresses and changing that what we call this pressure head in the water that reflects that loss of energy due to friction between the particles and the water. We may also develop what we call an excess water pressure, and this occurs when we have changes in external stress, whether that means you're adding a new layer of material on top of the ground surface, you're moving construction equipment across the ground, you're moving a pipeline over the top of a new area. When that change in stress occurs, there's going to be a volumetric response to that new stress, and it's going to manifest itself, at least initially, as an excess or an additional water pressure. Once again, we can still use that same equation, unit weight of water times pressure head, to define what this water pressure is. But once again, it is this pressure head that is going to change. Now, these two concepts together, total stress and water pressure, define what we call the effective or intergranular stress in a material. And the easiest way to explain, for me anyway, the concept of effective stress is to go back to Archimedes' principle. And what Archimedes' principle is telling us is that when we have an object that is submerged in water, there's going to be a net buoyant force that's equal to the weight of the water that this object displaces. That's how we get boats to float. And that same concept of buoyancy acts within submerged soils. So we can think of it this way, that if we take a particle of material, let's just say a particle of rock here, and we measure its weight is going to be defined as the unit weight of this rock or this mineral times its specific volume. So it's going to show up at a certain point on our scale here. If we take that same particle of rock and we submerge it in water, there's going to be a given water pressure at the top that is a function of gamma times the depth of water or the pressure head in the water, but there's going to be a higher water pressure acting on the bottom of that object, because at this point we're at a greater depth within the water, so the water pressure is greater, and that gives us a net upward water pressure or net buoyant force acting on this particle of rock. As a result, our weight that we measure with this scale is going to be smaller when this particle is submerged. Now, as of course, we don't have a bunch of big boulders in most of our facilities. We've got really, really small grains, but the concept is still the same. When we look at these as individual grains, the contact area of these individual grains, even for angular grains, tends to be only a very small fraction of the overall area of a given column of soil, for example. As a result, the buoyant force that is acting on any one of these particles is nearly the same as if you had that particle alone submerged in water, because the contact between the individual particles is such a small portion of the total area that is being covered by these particles. As a result, we can use this very simple form of this very simple equation to calculate this intergranular or effective stress as simply the total vertical stress minus whatever the pore water pressure is. And that pore water pressure is going to include any effects of flow, any effects of excess pore water pressures that are generated for a transient period of time. As I mentioned here, this is the most important concept in all of geotechnical engineering. If you understand this, you're going to be doing pretty well. Those stresses generally increase with depth. So I'm not going to spend much time on this, but this is a very important way to understand what those stresses are. We've got total stress here, pore water pressure, not considering negative pore water pressures or suction pressures above the water table, and then our effective stress here. Let's talk now about those engineering properties, or at least concepts. So let's start with consolidation. And I like to use a simple spring analogy to help students understand the concept of consolidation under load. So here we have this spring, where the spring itself represents our soil skeleton, or the compressibility of the material. The outside portion of this, or the fluid here surrounding this spring, is going to be the pore fluid. So most of the cases that's going to be water, but there may be ions in there, there may be salt in there, there may be other things in that pore fluid. And we've got here a valve that measures the pressure in the water at a particular depth. This piston here represents the overburden stress, and this additional port coming out of the piston that is controlled here by a valve is analogous to the permeability. In other words, the more open that valve is, the higher the permeability, the easier it is for water to flow into or out of, in this case, out of the soil skeleton. As you close that valve, the soil is less permeable, water has a harder time flowing out of that valve. So here, in this analogy, we're going to start with an initial total vertical stress, sigma V0. We're going to start with an initial pore water pressure, U0 or U0. We're going to start with an initial effective vertical stress of sigma prime V0, and the ground has not settled yet. Now we add some additional stress. Once again, this could be additional placement of tailings on top of existing tailings. So we've increased our total stress by an amount equal to the change in stress. That is for example, the height of a new lift of soil times its unit weight. Now, in the short term, and this is quite common with tailings, is that they are low enough permeability that they could be effectively idealized as having this valve nearly closed to begin with. And when this valve is nearly closed, there's not going to be any flow coming out of there. As you push this piston down, the piston isn't really going to go anywhere, because the fluid here has a very high stiffness or low compressibility compared to the overall soil structure or soil skeleton. As a result of not much water flowing out of there, the pressure in the water increases as we add that load. So here you see that pore water pressure jumps up to a value of U0 plus delta U, a change in the pore water pressure that is equal to the initial value of pore water pressure plus that change in total stress. Now, over time, water is going to start flowing out of this valve. Therefore, the load is going to be transferred. This change in stress is going to be transferred from the pore water to the spring, and the spring is going to start to settle. It's going to settle at a rate that is a function of how open this valve is, as we'll see in just a moment. So this soil, or this piston, is going to come to a new equilibrium point that reflects the new stress level and how compressible this spring is. Over time, that change in pore water pressure is going to drop to zero. That is, the pressure in the water is being transferred to the spring, or the load in the water is being transferred to the spring, and the water pressure is going to go back down to its initial value. And the effective stress now, because the stress has been effectively transferred over to the soil skeleton, is going to increase by an amount equal to the increase in total stress. Now, over time, there's going to be further settlements that we call creep or secondary compression. That is the continuing deformation that occurs under constant vertical effective stress. Let's look at this in terms of time-dependent behaviors. So once again, we're going to start with our initial total stress here, our initial pore water pressure, our initial effective stress, and in terms of settlement here, and I've plotted this two ways, arithmetically with respect to time and with respect to the log of time here. So this would be volume change or settlement on going downward here. So these are our initial conditions. Let's add in that change in total stress. So once again, we're adding a new lift of soil, for example. So this is being wished in place. So I've got this happening over 0 time. Of course, that's not terribly realistic. That's idealized too, but for the purposes of this discussion, it should do. In response to that, as I mentioned, because these tailings typically have relatively low permeability, the pore water pressure is going to increase by an amount equal to that change in total stress. There's going to be some initial movement here, initial settlement that's related to simply distortion of that material. So that's what we call immediate settlement that's related to the undrained compressibility of the material. Over time, the total stress is going to remain constant. We're not changing the thickness of the layer that's being added. We're not changing much else, but the pore water pressure is going to decrease over time as those excess pore water pressures slowly drain out of that piston or drain out of that cylinder. At the same time, or I should say as a mirror image, as the pore water pressure decreases, the effective stress is going to increase, because remember, our equation for effective stress is total stress, which here remains constant, minus the pore water pressure. So as pore water pressure goes down, effective stress will increase, and ultimately all of the load in the pore water is going to be transferred to the soil. At the same time, we're going to see settlement occurring. As those excess pore water pressures drain out, the particles move closer together in order to handle this additional load that has been placed on it, and the ground settles. The void ratio decreases, the ground settles. We call that primary consolidation. That occurs as excess pore water pressures due to a change in total stress dissipate. In arithmetic space, it looks an awful lot like a hyperbola. In semi-log space, this portion is more of a straight line. Over time, even though this effective stresses remain constant and our pore water pressures excess pore water pressures have dissipated, there's going to be continued distortion that we often call secondary compression or drain creep. And it's important to recognize that this movement is going to continue to occur, particularly as we look at INSAR data or other data that indicates movement of particles or movement of the ground surface, settlements, in other words, or distortions, that we have to make sure we don't mix up long-term settlements that occur due to secondary compression with distortional movements that are related to shear. We can predict what this primary consolidation and secondary compression settlements are going to be. Anything that's beyond that may be related to shear-induced volume changes. So identifying, predicting, and then differentiating those is really important to what we do. Just some additional details here in terms of how we calculate how long these settlements take. I want to spend the rest of our time talking about shear strength, because this is one of the key concepts that we have to understand. So we use a fairly simple equation to describe failure in natural soils. We have seen with a number of experiments that have been performed around the world on tailings that this Moore-Coulomb failure criteria works equally well for most tailings. And again, it is a simple equation that is related to a total stress here that is normal to a shear plane. We've got the pore water pressure here. So these two terms combined, again, are an effective stress. We have the tangent of the friction angle of the soil. And this relates to the friction that is developed at particle contacts. And we have an additional intercept here because as we'll see, this is a straight line equation when we use Moore Coulomb failure criteria to describe behavior. So these are the results from a number of tests. I'm not going to talk about the tests themselves, but rather talk about this straight line failure envelope that we call Moore Coulomb. The slope of this envelope is what we call the friction angle of the soil, drained or an effective stress friction angle. The intercept here, which most commonly does not represent real strength. Rather, it is solely an intercept from this straight line equation. For those of you who enjoy math out there, this equation is y equals mx. This should be m here. This is the slope, x plus b. So this is our intercept, this cohesion intercept in terms of effective stresses. So as we plot our shear stress versus effective normal stress, we see that the slope is our friction angle, the intercept is our cohesion intercept. Now, in reality, we rarely get tests that are this clean. More often than not, we get test results that do not quite line up, and we're going to need to run multiple tests to understand where this best estimate of this failure envelope falls. So we're going to use a best estimate interpretation of multiple tests to define these friction angle and this cohesion intercept. In reality, once again, further looking at reality, the failure criteria for soils is more curved than it is linear, particularly at high stresses, and particularly for finer grained soils like clayey soils and even slimy material that has some plasticity when we're talking about tailings facilities. This then does not satisfy this Coulomb. The Coulomb component is this cohesion intercept. So this curved envelope is what we would just call a Moore failure envelope. And we could describe this using a function, or we could describe it using secant friction angles that start from either our cohesion intercept or from the origin and decrease at higher and higher values of normal stress. Now, the next concept I want to cover is this drained versus undrained concept. This drained does not mean that there is no water in the soil. It simply means that there are no excess pore water pressures in the soil. It means that any shear induced or volumetrically induced pore water pressure or excess pore water pressures that may have developed have now dropped back down to zero. They have dissipated. And as a result of dissipating those excess pore water pressures, there is a volume change that corresponds. So this is delta, our change in volume over the initial volume, or the volumetric strain, is not equal to zero. And the reason I have not equal to zero here is because this volumetric strain may be positive or contractive, may mean a decrease in overall volume, or it may be an increase in overall volume or expansion, which we call dilation. It is common that coarse-grained soils that have high permeabilities reach this drain condition almost as quickly as we can construct things. So when you are building an additional lift of sand fill on top of an existing perimeter dike that consists of sand fill, even if there is water in there, as quickly as you can build that sand fill on top of the preceding sand fill perimeter dike, the excess pore water pressures are going to drain off, and it will be drained almost immediately. That is, we can also have this where we have lower values of permeability as long as the loading rates are very slow. You'll also hear the terms long-term, steady state, or effective stress condition associated with drain. But in essence, this means that the soil has either dissipated those excess pore water pressures, hence long-term, the concept of long-term conditions, or that loading is slower than the rate at which water can escape the soil structure or soil skeleton. On the other hand, undrained means that those shear-induced pore water pressures are not equal to zero. That is, as we load the soil, we saw for the piston analogy that as we load that soil or the tailings, that initially the stresses or the load is transferred to the pore water. That is true whether we are compressing that soil or shearing that soil. The load is transferred to the pore water commonly. And as a result, if the water pressure cannot drain off, if the permeability is low with respect to the loading rate, the soil generates excess pore water pressures. If there is no water escaping that soil skeleton, there's no change in volume, therefore our volumetric strains during that time are zero. So this is common for fine-grained soils that have relatively low permeability at normal loading rates, but it can also happen if our loading rate is relatively rapid, even in soils with higher permeability. And that's how we get liquefaction, for example, of relatively coarse sands, is if we have fast enough loading conditions, then even those sands cannot, the water cannot escape that sand structure fast enough with respect to the rate of loading, and we start to generate excess pore water pressure. We get undrained conditions. You also hear the concept short-term end of construction or total stress condition. But the keys here are the permeability and drainage path, which goes along with permeability. That is how fast can water move through the soil structure and how far does it have to go, the drainage path. Compressibility, that is how much water has to escape the soil, and how fast the soil is being loaded are the keys to whether the soil is likely to behave under a drain condition or undrained condition. So let's talk about what I mean by these concepts. First, we'll start with drain conditions. And I'm going to use triaxial compression tests as the example here. And these are tests that have been consolidated. That means they have some effective stress, and they are drained at the beginning of the shearing process as well as throughout the shearing process. So we're shearing these slowly enough that they do not generate excess pore water pressures. And these tests that I'm going to describe are performed at the same consolidation or same confining stress. So let's start with a loose sand behavior. As we take that loose sand, and so I like to use my my knuckles as an analogy here. We have a loose sand. You can picture that as your knuckles being relatively far apart here. As we shear that soil, your knuckles want to fall into the open space between that was existing there. They want to densify or contract in order to carry that load that's being placed. So what we see here is that the deviator stress increases as we shear the soil, as it undergoes axial strain. At the same time, those particles are falling into the open spaces and generating more shearing resistance. And that happens until the change in volume starts to level off. When we talk about a dense sand, a couple of additional points here. This would be a ductile stress strain response, and ultimately it reaches a constant value of shearing resistance and a constant void ratio. In other words, there's no more rate of volume change. The rate of volume change here is zero. The volume change curve is leveled off. We would call that the critical state condition. When we talk about dense soil behavior, we can use our knuckles again as the analogy. We're going to start with the case where you've already got your knuckles packed closely together. That is, you've already got the knuckles in the open spaces that loose sand fell into. Now, if we shear in this case, what happens is, as you see here, my knuckles have to ride up and over one another in order to start shearing. If you go through this exercise, you can see that first they look for somewhere to contract. And so during this process of looking for somewhere to contract, it starts to generate shearing resistance as those particles try to move past one another. As the soil finds that it has nowhere left to go, it tries to ride up and over its neighbors. So during this process, there is expansion or dilation of that volume of the soil structure. The soil continues to dilate until those particles do ride up and over their neighbors, and then the volume change levels off. As this soil continues to dilate, the soil goes through its peak, which corresponds to the maximum rate of dilation when the soil is doing the most work. That is, it's got to lift all the overburden stress. In order for those particles to ride up and over their neighbors, it has to lift everything above there. So it does a lot of work and generates a peak shearing resistance here. But then as things start to slow down and dilation starts to exhaust itself, the soil is becoming looser and looser during this process, right? We went from something dense with a lot of contacts to something much looser with fewer contacts. So that means the shearing resistance is going to drop. We would call this our peak shearing resistance. The soil undergoes strain softening and eventually reaches this same critical state that the loose sand did when we start at the same consolidation stress. In terms of void ratio, since we were talking about that dense sand, we'll continue here. There was an initial decrease in void ratio, and then the void ratio increased. That's why our strength ultimately went down. This is going to show a peak shear strength or shearing resistance at small strain. It's going to be relatively stiff, undergo that strain softening during dilation. That this would be this condition, what I described as dense sand, would apply to things like compacted sand tailings that have little fines. So a lot of our perimeter dikes may be constructed of compacted sand tailings. That's going to behave like a dense sand. That loose sand, on the other hand, remember, contracted throughout shear. It started loose and all the particles fell into the open spaces. Void ratio goes down. It generates its largest shearing resistance at large strain. That has, it's a strain hardening or ductile response, and it's almost all contractive. This would be the sort of behavior that we would expect to see in a slurry deposited sand or silt tailings. Now, this critical void ratio is the void ratio that both the loose and the dense sample ended up at after large strain. This critical state void ratio is unique for a given gradation and effective stress, and we're going to determine this experimentally. How about undrained behavior? So I'm not going to go through quite as much detail, but what I do want to highlight is the volumetric tendencies. That is, the soil wanting to contract or wanting to dilate is going to be the same when we start with a loose sand versus a dense sand. So here in orange again, I have the loose sand. In blue, I have the dense sand behavior. And rather than the soil actually changing in volume, because we have turned off the drainage valve here, we have undrained conditions. There's no water cannot escape or enter the soil structure in this case. That tendency for volume change, either contraction or dilation, is going to manifest itself as a change in pore water pressure. So that loose sand that wanted to contract is going to generate positive pore water pressure. So as those particles want to fall into this open space, if that water cannot escape from the voids between my knuckles, it's going to push back on the particles themselves. We're going to generate positive pore water pressures that are pushing back. As that positive pore water pressure goes up, remember the effective stress goes down, and so we often see a loss in shearing resistance. That in the extreme case can be liquefaction of these loose sands, where we lose a significant portion of that shearing resistance because of the generation of positive excess pore water pressures. In the case of the dense soil, remember we started with it tightly packed here. It wants to ride up and over its neighbor, but if water can't enter that space, as those particles try to ride up and over their neighbors, the water goes into tension. If the water goes into tension, we get negative excess pore water pressures. That negative excess pore water pressure, remember from our effective stress equation, means that the effective stress is going up and the shearing resistance ultimately goes up as well. So once again, this dense soil is going to be higher stiffness and be strain hardening in this case. The loose soil in this case is going to have the contractive tendency. It's going to reflect as an increase in excess pore water pressures and going to be strain softening. But once again, these both reach a critical state condition. They both have a level off value of shearing resistance ultimately, and this volumetric tendency, which is manifest as an excess pore water pressure, also tends to level off at larger strains. So using those concepts, we know that the rate of pore water pressure and dissipation is a function of loading rate and the soil type. In other words, is permeability and compressibility. That shear stress or shear strength, effective stress, void ratio, those properties are interlinked and are going to be unique, as I'll show you, for a given soil. As the void ratio goes down, the strength tends to go up. As the effective stress goes up, strength also goes up. But when we're looking at loose, potentially contracted soils, that is going to be different when we have undrained conditions. So we need to understand how to assess that potential change in pore water pressure during undrained shear. And so we're going to use critical soil mechanics to help us understand that. And I'm not going to go through this slide in detail, but we are going to connect three spaces. We're going to connect void ratio, effective stress, and shear stress with these. And I'm going to use a simple space here of just void ratio and log of effective stress to do that. So when we start with this soil that is loose, remember that's with with the fingers separated or knuckles separated. If we shear under drain conditions, void ratio goes down, and this point then from our initial condition would go down to a certain void ratio. If we shear under undrained conditions, remember the particles can't move closer together or water pushes back, so the effective stress goes down. Both of those end up on this critical state line from an initial contractive condition. On the other hand, we can start from the dense side. Remember, pack your knuckles together and do this. And as we shear this under drain conditions, the soil increases in volume, it dilates, so the void ratio goes up to the same point here at this when we start at the same effective stress, even though the void ratios here on the y-axis are very different. If we shear the soil under undrained conditions, as the soil wants to dilate and go up and over its neighbors, water cannot enter, so the soil goes into, or the water goes into tension, the effective stress increases and reaches this same point on this critical state line. So this critical state line is a way to differentiate what we would expect to get contractive response, either drained or undrained contractive response, or dilative response. I'm showing it here in on two axes, or in void ratio, effective stress space. But in reality, as I mentioned, this critical state line is really a function of three variables: void ratio, effective stress, and shear stress. When we plot this in arithmetic space, that straight line becomes a curve. So let's look at one point here on this critical state line. If we project this onto the the void ratio effective stress plane, which is what we were just working with, that straight line, when it was log of effective stress space, becomes a curve in this void ratio effective stress space. We can project that onto the shear stress void ratio space. That's telling us as the void ratio decreases, the shear strength increases. And we can project that onto the shear stress normal stress plane as well. This is the friction angle of the soil. This is the slope of how the shear strength changes as the normal stress changes. So this concept of CSSM is pretty powerful. And we're going to use a few additional parameters, one of which is a state parameter, which tells us the distance from the in situ condition to the critical state line, to give us an idea of whether we would expect contractive or dilative response. When we have positive values of state parameter, we would expect contractive response. When we have negative values of state parameter, we would expect dilative response. When that state parameter is close to zero, we might expect limited flow. Now, I've got just a couple of slides left here. I will go over these relatively quickly. We look at what this means in terms of undrained behavior. I want to highlight one thing here. We have here three tests, all performed at the same consolidation stress, but different void ratios, which corresponds to different state parameters. Here we have a value of 0.04, a value very close to zero, and a negative value, not very large, but a negative value. And you can see these different state parameters, contractive here near the critical state line, and dilative here, result in very different stress strain responses, with positive values being cases where the soil is potentially liquefiable. So to summarize, as we talk about from slurry to soil and geotechnics, we really are focusing on engineering properties. The two that are very important are compressibility and shear strength. And we want to characterize those so that we understand the behavior of one side, but also understand how other sites might perform in the future. And as I mentioned, we need to think about this in terms of index properties, geochemistry, as well as our engineering properties. So with that, I'd like to thank you for your attention. And as I warned Chris as I got into this, I normally don't leave much time at the end. I think I'm right on time here at the end, Chris.
Right on time, Scott. Perfect.
But no time for questions.
There were a couple questions. We can forward those along to you and bring them up in the panel discussion if they seem appropriate. But with that, thanks so much, Scott. A lot of great content there. So we'll take a short 15-minute break, and we'll be back to pick up right where we left off and start talking more about critical state soil mechanics and the importance of mechanics. So thanks, everyone. I'll see you back in about 15 minutes. Thanks again, Scott.
Thank you, Chris.